Hi everyone. I'll kind of sit up here, having a few technical issues at the moment, so we're really sorry about that. We're going to just quickly sort this out, and hopefully you've had access to the PowerPoint and some of the other bits. You can look through the content already. We're hoping to get this all sorted in the next few minutes and come back on at 6 o'clock. So apologies for that. I don't know if the message has come through to you yet, that you can only see half my face and we want to be able to see the whole PowerPoint. Yes, thank you to all of you that are already here and messaging in and ready to start. We'll be as quick as we can. But as I said, if you could be ready for 6, that's what we're aiming for, and we'll keep you updated. Is the sort of Zoom looking a bit weird, or is it kind of in place? I'm just checking if the technical difficulties are fixed. If you can see me, great. Let me just check. Can you guys see and hear me? Please let me know in the chat. Oh, okay. I think we've sorted it. So no, don't come back. Stay here. Welcome, and sorry about the delay. Let's just check we're all good and we can all see it okay. It was a bit of a mad panic there. That's great. Okay, sorry guys. Sorry about the delay there. And thank you all for being here, and great, that looks fine. So we're going to get started. I'm about to share my screen. Hopefully you've had time to look over what we're going to cover today. Look at the topic is roots, and we've sent some stuff in the chat. And I'm about to share my screen and get started. Thanks again, and I'll keep it open so I can see all your messages. But as I said, apologies for the delay there. And yeah, welcome. Right, I'm going to share my screen and not waste any more time. 1 second, and we'll get cracking. So share screen, and if you could let me know in the chat that you can see my PowerPoint, that would be brilliant. Can you guys all see that okay? We're going to be looking at roots today, and I'm going to make it full screen. Make sure that's all viewable. Okay, and just so I know, so I can get started, is the display of that, is the view all okay? Can you see the full screen? And thank you, Evan, and who else has replied. Is it cutting anything off, or have you got the full view of what I'm showing? Oh, excellent. Okay. Brilliant. Thank you so much, guys. I was a bit concerned that you were only going to see half of the words. So yeah, that's fine. Excellent. Right, I'm going to get started, and thanks again for your patience, guys. We're going to get cracking through here. So as I said last week, I'm Max. I'm head of maths at Snap Revise, and I've been teaching maths for the last 4 years at A-level, at GCSE and Key Stage 3. What we're going to do today, we're looking at a GCSE topic, kind of higher tier maths topic that is really crucial for the GCSE, but also comes up at A-level as well, and is just a really important idea, very pure maths based. So what we're going to look at today is the idea of roots. I'm just going to whiz through this bit. So a bit about Snap Revise and what we've got coming soon. We've got lots in place for GCSE tuition, all tailored to the new GCSE, lots of classes every week, and the whole curriculum really finely covered to every sort of detail. So you may be aware that the GCSEs and A-levels changed sort of fairly recently, and Snap Revise have been really on top of all the tiny changes to the curriculum. So it's all really tailor-made and kind of perfectly done to help you with your course. So excellent. I'm going to quickly explain what we've got coming up. So again, same as last time, I'm going to do 10 accounts given away if you enter in your email in the link, so that once we end this competition, we'll be giving away some accounts to allow you to have access to our platform and the kind of abundance of resources that we've produced to help you with your GCSEs. So that's hopefully really exciting and something that you might consider signing up for. And as I said, thank you all for being here and being so patient today. So do definitely sign up for that. And I'm going to get started with what we're looking at today. So a competition link has just gone into the chat, and we're going to get cracking with roots. So what we're going to look at is what a fractional power is, apply index laws to fractional powers, and estimate the values of roots. I'm not going to do a lot on surds, although it will sort of come into it, how surds work and what they are in terms of fractional indices. So fractional powers, when I was at school, I was just taught a load of rules for it, and I was never really kind of taught exactly why and the reasons for these rules. So I want to go into a bit of that today. What we've got is all of the exam boards are covered. This is a topic that's fundamental across all exam boards. So anyone doing the GCSE maths will need to understand how powers and indices work. Right, excellent. So what I'm going to do to start with is just kind of explain the background of this. And please do share answers in the chat for this. So I'm going to just quickly annotate, and hopefully you guys will be able to see my annotations on here. So if I, for example, were to work in powers of 2, so I went to 2 to the 0, 2 to the 1, 2 squared, okay, so 2 to the 0, those of you that have done this, you might have learned before that anything to the power of 0 is actually equal to 1. Let me know if you're familiar with that. A number to the power of 0 is 1. And when I covered it, I was taught it as a kind of rule, just learn something to the 0 is 1. Let me know if you're familiar with that, but I'm going to hopefully shed some light on why this is, why that makes sense. So who has seen that powers of 0 mean that we have 1? Excellent. Lovely. Yeah, so it's just like loads of rules. It just feels like I've just got to know that for the sake of it, if they put something to the 0, I have to just write 1. And that never really sat well with me. I didn't like that. I didn't like that I had to just know loads of rules for no reason. I wanted to understand it. So 2 to the 1, okay, we can accept that anything to the power of 1 is just itself. And anything squared, if you've done squaring numbers before, 2 squared means 2 times 2, and then we've got 4. And then if it was 2 cubed, we'd go, okay, so that's 2 times 2 times 2. And so that would be 8. So actually, once we do squared and cubed and to the power of 4, it actually makes a bit more sense. But what I'm going to show you is that essentially what we're doing as we go up the powers of 2 is we're essentially timesing by 2. Times by 2, I'm timesing by another 2, I'm timesing by another 2. So as I go down the powers, what am I doing? I'm going from 8 to 4. I'm essentially dividing by 2. So as I go down the powers, when I divide by 2, I divide 2 by 2, I get 1. That is why 2 to the 0 is 1. Because it's 2 to the 1 itself divided by 2. So it's the base number divided by itself. The thing to the power of 1, which was itself divided by itself, will always equal 1. So if I take that idea a little bit further and I go 2 to the minus 1, I divide by 2 again. If I divide by 1 by 2, I get a half. And if I go further still and divide by 2, I get a quarter. And so what we have is these negative powers start mirroring the positive powers in the denominator. So what that means is, as the powers increase, so for example, 10 to the 0 is 1, 10 to the 1 is 10, 10 squared, you'll all know, is 100, 10 cubed is 1,000, and that kind of makes sense. I think 10 is another nice one to look at. And as you go up the powers, you add a 0, you times it by 10. But as you go down the powers, you divide by 10. So that's why when we get to 10 to the 0, we are doing 10 to the 1 divided by 10, which is just 1. So if I went 10 to the minus 1, it would be a tenth. If I went 10 to the minus 2, it would be 1/100th. 10 to the minus 3, 1,000th. And so going down the powers, I'm dividing by 10. So that's why negative indices, negative powers, it basically mirrors the positive powers, but in the denominator. So it kind of explains why anything to the 0 is 1 and anything to the minus 1 is 1 over. Yes, so square rooting a negative, that's a little bit of a sidestep, but I will talk about that because we are going to look at square roots in a minute. Absolutely, you can't square root a negative nicely because 2 negatives times together makes a positive. So there's no way of getting a number to times by itself to make a negative. So hopefully that's answered your question there. But I can come back to that after if once we get through this, if that's needed. So basically you can't find two things times by themselves to make a negative. Right, so as I said, indices going down the powers, the negative powers mirror the positive powers in the denominator. Brilliant. Right, welcome to anyone that's joining. Now, what we're going to look at today is if we think about this, if we take, for example, the nth root of a, and we call that b, so that means maybe the square root or the cube root or the fifth root. Are we happy that b to the power of n would equal a? So, for example, welcome, hi, excellent if you've just joined. What we're just doing is going through some key ideas, and then we're going to do loads of examples and get you nice and exam ready for this topic. So if I take, for example, the square root of a is b, that would mean b squared is a. If I was dealing with the cube root of a is b, then that would mean b cubed is a. Does everyone kind of get this point? Do let me know if not. I'm happy to clarify if that is a little bit unclear, but please do let me know if that makes sense. And what we're going to do is really extend this idea today. So this is certainly a higher GCSE topic. Excellent. So for example, let's just go through some nice square roots that we should know. So square root of 4 is 2, because 2 times 2 is 4. Square root of 9 is 3. Square root of 25 is 5. And the fourth root of 81, well, I know 9 squared is 81. So can anyone work out? Excellent. If you know 9 squared is 81, this is the fourth root. Something times itself, times itself, times itself. So this will actually be 3. So the square root of 81 is 9, but the fourth root is 3, because 3 to the power of 4 would be 81. 3 times 3 times 3 times 3. So we've just got to be really clear on that notation of the roots as well. So if it just has root, that means square root. We're a bit lazy with square roots. We don't put a 2, we just write the symbol, and that means square root. If we put a little 3 or 4, that means the cube root or the fourth root, and so on. So just an indication from you that that's clear, a little thumbs up, a yes or a no if not, but just to give me an indication that that's all okay, and we'll get cracking with some of this higher tier content. Just give me a sense of where you guys are at, but hopefully that's all cool. Lovely, brilliant, and I'm going to step it up and move on a little bit now. So what we've got here, again, I know we get into this feeling of it's lots of learning rules and so on. Brilliant, thanks for the reactions, guys, that's lovely. So what we've got is a to the power of n, is essentially a times a times a, blah, 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 times a, basically n times. That's what that means, times itself n times. It's very easy. A lot of people, I'm sure you're aware, make the classic mistake of thinking a squared means times it by 2. It doesn't. It means times it by itself and have the multiplication twice. So if it's a to the 10, it means a times itself 10 times, not 10 times a. Now, can anyone tell me what this one would be as a power of a? And again, it extends on that idea. Well, I'm doing a times a times a times a, blah, 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 n times a times a times a, blah, 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 m times. So essentially, how many times have I times a by itself? N plus m. So this is weird. This is where the rules, we really want to make sure we understand them and not just learning them for the sake of it. Exactly. So you need to add them, because it's basically like a times blah, 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 n times multiplied by a times a times a, m times. And so if I times that all together, I've got n and m added up as the amount. Yeah, brilliant. So in a similar way, can anyone remind me what this rule would be? So this would be for division. So another thing that we hopefully got as a bit of prerequisite knowledge for this is that this one, in a similar way, if you were to cancel it out when you divide, this will be a to the n minus m. Okay, excellent. Now this is the one that people confuse with this rule. if you've got a to the n times a to the n times a to the n m times, then basically, like, imagine it was 3 and 4, you've got 3 times 4, so you times the powers together. So when it's a power to a power, you multiply and you get a to the nm, or mn, same thing. You multiply them. Very well done. Thank you guys for all the answers that are coming in. This is brilliant and helping me speed up the pace here. This is lovely. This one, as we've just seen, is 1 over a to the n, which is hopefully kind of prerequisite stuff we've seen. And just with some examples of this, if I just quickly whiz through, that would be 8. That would be 2 to the 3 plus 2. So that would be 2 to the 5, which is 32. This is basically 2 to the 3 minus 2, which is 2 to the 1, which is 2. This is 2 to the 6, because we times it together. This is 1 over 2 cubed, which is 1/8. And we're going to do some full-on exam practice now, really tease out this idea with some specific examples. Excellent. Right, let me move on. So here we go. Let's look at fractional indices now carefully. So here we go. Let's have a little look at the first sort of slide of notes. So a fractional index, an index being the power, represents the, and I'm going to say nth root. It represents a root of a number, and I'm going to explain why. Because again, this is one of those things that people feel they have to learn as a rule, but it doesn't always sit right. So if I want to show that the square root of 5 is 5 to some power, let's have a little think about that. Can you guys tell me what I would get if I did square root of 5 times square root of 5? Because imagine that is essentially 5 to the k times 5 to the k. Yeah, exactly. Excellent. I would just get 5. The square root of something times itself would just be 5. So what I would get is I would get 5 is equal to 5 to the power of 2k. Okay, so that seems a bit weird. So if I'm trying to solve what k is, well, if 5 to the 1 equals 5 to the 2k, that must mean that 2k equals 1, which means that k is equal to a half. So for this scenario to work, the only way it can work is if k is a half. Because when I have something to the power of a half times something to the power of a half, and I add the powers, it makes the thing to the power of 1, indicating that 5 to the power of a half is just another way of denoting its square root. So, and it becomes, yeah, exactly, it becomes 1. It just becomes 5 to the 1, which we want. So another way of representing the square root of a number is essentially saying that number to the power of a half, because I know that when I times two numbers to the power of a half and I add the halves to make 1, it gives me the number. So in turn, that number must be the square root. Please let me know if that does make sense. It might be something you knew anyway. It might be something you were aware of before. But if not, hopefully we can really tease that out and just make sure we're kind of shedding some light on that. So fractional indices, square root, means that we're basically doing the power of a half. If I times it by itself and I add them to make the number to the power of 1, that would mean that the power of a half is essentially the square root. Yeah, it is a little bit confusing, especially if you've just learned it as a rule. Oh, that's lovely. Well, we'll hopefully get through this and make sure that we can really tease out these ideas, because I know that when I first learned this, it just seemed like too many rules and I wanted a clear definition of it. So let's go through and think about how this works then. So I've got some powers of 5 here. I know that if I start with powers of 5, so 5 to the power of 0, that would be 1. Then in between, if I had root 5, and then I went here, and then I went 5 root 5, and then I went here, then what we've basically got is that that's 5 to the 1, that's 5 squared. So basically what we've done is by timesing by root 5, this might help as well. We've basically used the half power, power of 1, the power of 1 and a half, the power of 2. So you can kind of see how it links you from 1 to 5 in this sort of doubly multiplicative step. The only way you can jump up to the power of 1 in 2 steps is if the square root of 5 was the half power. So there's lots of different ways you can sort of tease this out. Some people just go, do you know what, I'm just going to learn that the power of a half means the square root, the power of a third means the cube root, and they can kind of commit that idea to memory quite easily. But it does often help us if we can think, well, what does a power of a half really mean? It means that number times itself gives me the thing to the power of 1. So if I've times it by itself, it must be the square root. And we'll see this with more examples and hopefully really bring it to life. So please do keep me updated in the chat if it's still a little bit unclear, or you think I'm not sure, or I'm just going to learn this rule. Lovely, thanks for the comments, guys. We're going to crack on through loads of examples here to really make sure we're fully confident with this idea. So let's have a little look at this next one then. What I'm basically saying as a given rule then is if I've got a to the power of 1 over n, that means the nth root of a. So if I had a to the half, it would mean the square root. If I had a to the power of 1/3, it would be the cube root. If I had a to the power of a 10th, it would mean the 10th root. What number times itself 10 times gives me a? So a really interesting idea. Obviously, if it's a calculator paper, this is great. You can plug it directly in. But understanding this is really crucial, especially sort of for a non-calculator paper. I've seen on numerous occasions students go into the non-calculator exam and the first question is something like this. So they know that this is a challenge for non-calculator. So you can kind of be exam ready and think about gearing your revision up to, okay, if it's a non-calculator paper, this is quite a likely topic. If it's a calculator paper, probably not so much. Now this one, I'm just going to explain. Hopefully everyone's happy that m times 1 over n is the same as m over n. If you had a fifth times 2, you'd have 2/5. So you could break it up like that. So this is basically the nth root of a to the power of m. And we're going to see this with some numbers now. It'd be great to hear some of your answers in the chat for these questions. So for example, 2 to the half, you might think, that's a bit tricky. How do I do that? You can leave that as a surd. You can say, well, that just means the square root of 2. What about this next one? What would we have here? 3 to the quarter. This would be the 4th root of 3. Okay, and they might not be nice numbers. They might be decimals, so we could just leave them like that. Can anyone tell me the answer to this question here? What is this one? This actually ends up nice. Yeah, lovely, Amy. Thanks for that. Excellent. This is the square root of 16, which actually comes out as 4. Superb. What about this one? I think we've done this one over here. 81 to the quarter, which is the 4th root of 81, which, does anyone know what that is? So we're looking for the 4th root of 81. The number that multiplied by itself 4 times gives us that. Superb. Thank you to all of those that are sharing answers here. That's lovely. It would be 3. Well done. Now, well done. I've seen some people answering some of the later questions as well. So 7 to the power of 5/6. So this means the 6th root of 7 to the power of 5. Really well done. And yeah, excellent. Hats off to whoever answered that. It's not, almost, yeah. It's not easy to write that in a chat. So very well done for that. It's the 6th root of 7 to the 5. Absolutely. Now this one, this is nice. Well done to those that have already suggested something for this. This is actually okay to evaluate without a calculator. So I think it's very similar to questions like this that I've seen in the non-calculator paper. Very well done. And you would expect actually that it gets to a bigger number. So if you're sort of sense checking your answer, does that seem feasible? Does that seem sort of legit? Could that work? Yeah, it could. If you've got a number that's bigger, we are hoping for that. We are anticipating it's going to come out more than 25. So it's the square root of 25 cubed, which is essentially 5 cubed. So 125. So very well done if you got that. That was great. I'm going to carry on. And thank you again to everyone working so well in the chat here and allowing us to power on through these questions. Oh, see what I did there? Power on. Okay, that was a bit of a lame one. Sorry about that. Okay, 2 to the power of a third. What does that mean? What does this mean here? What have we got? 2 to the power of a third. Excellent. Yeah, good. It's the cube root of 2, okay, which isn't a nice number. So there's nothing wrong with leaving it written as that. That's the sort of exact mathematician answer. There isn't, you could use a calculator and round it to some decimal places, but that is the exact answer. So that's absolutely fine leaving it as a third. Who here has had questions before where their teacher has said, leave it as an exact answer, give it as an exact answer, give it in terms of pi, leave it as a third? Because I know that when I first saw that, I felt like it seemed a bit weird writing it like that. I like to give it as a decimal and kind of understand the number's magnitude a bit more. Yeah, and it feels weird, but from a mathematician's perspective, that's fine. Cube root of 2, I know what that means. Don't know exactly what the decimal is, but yeah, and I know that that's actually a real sticky point for students. They kind of think, well, I want to know. I want to know the decimals of places. I kind of want to give an answer that normal people would understand here. But there's nothing wrong with leaving that as the cube root of 2. That is the exact answer. Well done to those that have answered these other questions as well. So the next one here would be the 4th root of 5. Leave it like that. You could give it as a decimal if it said to 2dp to 3sf in a calculator paper. If it doesn't, let's leave it like that. Brilliant. Next one. This one here, a bit like the one we did with 25. Excellent. It's the square root of 2 all cubed. Okay, and there's other ways we could do that. That's like square root of 2 times square root of 2 times square root of 2, which you could potentially write in a couple of different ways as well. I'm going to keep going. So 7 to the half is the square root of 7. Lovely. It's a third. We'll leave it like that. The next one is the cube root of 3. Well done. And well done at the speed some of you are writing these answers in. It's lovely to keep checking the chat and seeing all these answers coming in really quickly. So this one is the 4th root of 5 cubed. That's fine. We'll leave it as that. We've got to get used to writing it in a way that we don't always like. This one actually evaluates nicely, doesn't it? Square root of 49 is, someone's going to say it hopefully in the chat, square root of 49, what times itself is 49. So that one is a nice one, lovely, it's 7. Cube root of 27, this is actually a nice one to evaluate. Does anyone know what the cube root of 27 is? What times itself is 27? Absolutely, well done guys to those of you in the chat. Keeping this momentum going, this is lovely, it is 3, well done. Now this one is quite interesting. I'm just looking at the questions here, but some good questions coming in. Can we put the power on? I'm not 100% on what we mean. If you could have another, just clarify that question a bit and I'll be happy to answer that. I'll just finish this one quickly. So what we're doing with this one is this is the square root of 9 to the power of 5. Now the square root of 9 is actually 3. So this is another way of saying 3 to the power of 5, which is actually 243. Okay, lovely, excellent. Lauren and whoever's named after a calculator, that's lovely. Actually got a class whiz on here, that's great. Excellent to all of you who have shared that answer, that's brilliant. Please do ask the questions though. I know a few people have questions and I'd like to clarify some things for them. So if you could let me know if things are still unclear. We're going to keep going because I think we're doing really well here. That's great. So let's keep going. Now this one, this is a kind of question we might think, oh no. And the thing that probably would have scared me at the time of GCSEs would be, I'm doing maths, where are the numbers? And I understand that completely. I've been through that experience myself. I know what we're all thinking. X to the A over B times X to the C over D. We're supposed to be doing maths here. Where are all the numbers? We're looking at a very general case that's very algebraic and is really testing that we understand the idea more than can we do stuff with numbers. So let's have a little look. any suggestions? I know this could be quite tricky to write in the chat, but they're both powers of x. So the answer is, hopefully we're going, well, I'm going to have a shot here. It's going to involve x. X to the what? What do I do to powers when they're the same base and I'm timesing? We looked at the rule earlier. We add the powers. So what we would do here is we would add a over b to c over d. So what we're going to get is, and I'm going to write that in general, that would basically just be this. And you could write that as a combined single fraction using common denominators, but that is essentially it. Don't forget the key rule that's going on here. Doesn't look lovely. Let me just see that question right. It's square root of 5 cubed. Oh, okay. Yes, I see what you're asking. Yes, and I will clarify, that's a really good question. I'm going to come back to that in a minute. Excellent. Yes, the order that you do the things, are they the same thing? I'll show you that in a second. Yeah, that does work. Great, so this one, which will be a over b minus c over d. Now this one we're timesing, so this will be, oh, hang on, this would be x to the ac over bd. And you might be like, yeah, I'm following, but doesn't feel like my favorite thing. Well, let's make it your favorite skill. If we know these rules well enough, we can apply it even if it's algebraic. Okay, so the next one, any suggestions for 2 to the quarter times 2 to the 3/4? This is actually quite nice, this one. And sorry if you've already answered this. I don't know if people have already put something earlier in the chat. I don't think, from what I can see, anyone's done this one specifically. 2 to the quarter times 2 to the 3/4. You add them. Yeah, go for it. 2 to the 1. So interestingly, this is actually just, the answer to this is just 2. Okay, and we never even needed to worry about what 2 to the 3/4 was and what 2 to the quarter was. It comes out as 2 to the 1, which is 2. Well done, excellent. So very good. So this next one is 3 to the 3rd divided by 3 to the 2/3. So that will be, if we do 1/3 minus 2/3, then what this comes out as is 3 to the power of minus 1/3. And we'll look at that a bit more in a minute, because that feels like, well, that's a bit weird, but that is just obeying all the rules, and that would work. Excellent. Right, let's keep going. So this next one, we're going to times them again. So it's going to be 5 to the power of 12 over 14, which actually you can still simplify fractions. That is essentially 5 to the 6/7. Well done. Cool. Excellent. Now, I do want to clarify those questions that we had there, and I think I will have a few slides in a minute that really do tease those ideas out. So I will come back to that question. Don't think I've forgotten. I just want to go through this in a kind of nice linear fashion and make sure we hit everything. So yes, we'll clarify that, but it was an excellent question. So here what we've got is, for this first one, hopefully everyone can see that, 5 to the 3rd, and then we're basically timesing, so we're adding the powers. 1/3 add minus 1/3 ends up as 5 to the 0. What's that equal to? Yes, excellent. The calculator's got in there first. Well done. That is 1. Lovely. Well done. Now this next one, what we've got here is we've got 2 to the power of 3/4, and we're going to minus 1/4. So what we end up is 3/4 minus 1/4 is a half, essentially, isn't it? It's 2/4, which is 2 to the power of a half. And let's remember what that means. That means the square root of 2. Okay, so that is right. That is the answer. But remember, we can also present it like that. So just look at how they might ask for you to present it. Now this one, I think this is the question that someone was asking about there earlier. Is that the same? Is 7 squared to the power of a 5th equal to 7 to the 5th squared? And it actually is. The order you do it doesn't matter, because essentially what we're going to do is times the 2 together. So 2 times a 5th or a 5th times 2 are the same thing. It is 7 to the 2/5. So absolutely, I hope that answers the question. Does that make sense? Please give me an indication that that sort of clarified that the order of that works. Oh, welcome, thank you, that's lovely. Right, brilliant. Some people are just carrying on with more of these answers. Lovely. Right, so the next one here is 3. Now this is interesting because this is 3 to the 1 times 3 to the half. So that's actually in itself, that could be tidied up as 3 to the 1.5 or 3 halves. It depends how we prefer writing it. Maybe let's say 3 to the 1.5 or 1.5, however you want to write that, times by 9, which is actually 3 squared. So I've got 3 to the 1.5, and hopefully we're happy that 1.5 is the same as the improper fraction 3/2, and I'm timesing it by 3 squared. So as a single power of 3, I'm adding 2 and 1.5, which would be 3.5. So 3 to the power of 7/2, or 3 to the power of 3.5, or 3 to the power of 3 1/2. So that one was a little bit tricky. Yes, absolutely. So GCSE, any equivalent of that O-level, higher maths at GCSE standard, this stuff is really crucial for all exam boards. So quite an important topic. And as I was saying to people earlier, oh, good question there. 27√3 be correct? That's an excellent question. This is the same. So as I said, this is the same as 3 to the power of 3.5. Now, 3 to the power of 3 is 27, and 3 to the power of 0.5 or a half is the square root of 3. So excellent, and like I need to say congratulations, but it is kind of congratulations. That was superb. Maths there, that those that work that out, that is absolutely equivalent to 27√3. That's lovely, and that's something we should be looking for. Could we do that as well? Could we write it that way? Thank you for asking that and clarifying. That was brilliant. As I was saying earlier, this skill is very likely to be a non-calculator skill, and it's really the understanding of it that we want. Okay, so let's have a little look at the next one. So what power, a power of what number is this question lending itself to using? So we've got the number 16, number 4, and number 2. So is there a number that we could write it as a power of? And there might be multiple ways we could actually do this. I'm going to suggest that they're all actually powers of 2. So let's use 2. So let's think of 16 as 2 to the power of 4. And I'm dividing it by this, which is 2 squared times 2 to the half. So basically I'm doing 2 to the 4 divided by 2 to the 5/2, or 2.5. And then I'm going to do the subtraction. So that's equal to 2 to the power of 4 minus 2.5, which is 2 to the power of 3/2, or 1.5. And well done to those that have said, is there another way you could write that? There absolutely is. 2 to the power of 3/2. As someone asked earlier, that's the same as 2 cubed squared, square rooted, or square root of 2 cubed. They're the same thing. So you can think of that as the square root of 8. That is another equivalent way of writing it. Right, who spotted the trick with this? This one is actually, if you spot the trick, it's actually a really easy question. Oh, good, I'm seeing some questions coming in, and welcome to those that are just joining. How did you get the power of 2.5 from fourth root of 2? Oh, good question. So, I see what we're saying there, Lauren. Good question. This is not the fourth root of 2. The fourth root would be if it was a little 4. This means 4 times the square root of 2. That's a really good thing to look out for, because I'm sure there are others that thought the same. That doesn't mean the fourth root. We've got to be so careful with notation. Just like how this didn't mean the cube root, it meant 3 times the square root. It's only if the 4 is little like this that it would be the fourth root. So in this question, it's the fourth root, but can you see that this means 4 times, which is not the 4 times the square root as opposed to the fourth root? Does that make sense? Whoever was asking that, Lauren, that that is 4 times the square root as opposed to little 4, which means the 4th root. Does that make sense? Excellent. Thanks for clarifying that. That was really good. Hopefully that clears it up. Yes, this next one, 6 is the answer. And there's a few ways I can see in the chat that people are explaining this and sort of teasing this through. You could think of it as 6 to the power of a quarter to the power of 4. 4 times a quarter is 6 to the power of 1, which is just 6. That's a nice way of doing it. Or I'm basically 4th rooting something and then doing the power of 4 to that. So it's like the inverse function, the inverse operation as well. If I square root and then square it, it just takes me back to where I was. Hi, welcome. It's great to hear people from across the globe tuning in and joining us for what is really a crucial topic. And so lovely to see how well you're working in the chat and suggestions you're making. I'll talk a bit more about the live classes later. At the moment, these are weekly sessions, but there are lots of live classes running on Snap Revise on the platform itself. So if you're interested, we are doing 10 accounts are going to be given away for free, as I mentioned at the start. So if you are interested, as I said, YouTube, we're going to be doing that every week for now on a Wednesday at this time. Right, I'm going to crack on. Could you give me an indication, 1, 2, or 3? Very minimal amount of maths here, just to tell me how you're finding this. So just a quick indication of all right, straightforward, or super confused. Hopefully we're all x to the power of 0. See what I did there? Maths jokes, I think they're getting worse. Yeah, we're hopefully fairly straightforward, but I hope you haven't super confused anyone. But lovely, yeah. So that's good. Well, that's good. Do let me know, 1, 2, or 3, how you're feeling. We're going to crack on with some actual exam questions now and see how we get on. Lovely. Here we go. Where are we at? Now, this is an interesting one because please do share answers if you think excellent answer there on how you're feeling. Well done. 125 to the power of minus a third. This could be straight away a GCSE question. Evaluate, work out the value, non-calculator. What does that mean? There's a few things going on here. What do we do with that? 125 to the power of minus a third. Excellent. Okay, right, this is nice and reassuring. Thank you, guys. Excellent. This is basically, like someone asked earlier, there's 2 things going on. There's a negative aspect to the power and a fractional aspect. So there's this sort of flipped version, this reciprocal thing, and there's also the cube rooting element. So it's basically, you could think of it as 125 to the third to the minus 1. Or you could think of it as 125 to the minus 1 to the third. So you could think of it as cube root and flip, or you could think about flip it, do the reciprocal, and then cube root that. Either way, it ends up as the cube root of 125 is 5, and then it's 5 to the minus 1, which is 1/5. So very well done. 2 marks in the bag for your GCSE straight away. Great work. Right, let's keep going. So another one here. I'm going to just move this on. Write these numbers in order of size, starting with the smallest. You must show you're working right. Let's evaluate each of those numbers then and see how we go. Good, yeah. Flipping it over, the reciprocal, the negative power, you are flipping it. So the negative flips it, the reciprocal. So there we go. 27 to the 2/3. What is that? So that is 27 cube rooted and then squared. Now, my bit of advice for you guys here is always do the fractional bit first, because it gets the nasty bit out of the way. You could square 27, but then you've got a cube root, a really horrible number. So I would always cube root it first, get it as small as possible, and then it's an easy number to square. So I would go, okay, cube root of 27. So a bit of an exam technique there. So we're doing the cube root of 27. Can we make that a bit clearer? Squared. So that's going to be 3 squared. So that's going to be 9. Well done. Lovely. And then we're going to do for this one, 64 to the 3rd. So that means the cube root of 64. What times itself is 64. That is actually 4. So we've got 2 of the values already. And 4 to the power of 3 over 2, that means square root it and then cube it. And I would probably personally do it in that order. Square root it first, then cube that. So it'd be 2 cubed, which is 8. And then we've got them. Obviously, this is the smallest, middle, largest. So first one, second one, third one. And then just to be in keeping with the question, let's write it in the way that they actually asked it in the question. So I'm going to write this one as 64 to the third is the smallest. The next one would be 4 to the 3 over 2. And then the last one would be 27 to the 2/3, 3 marks. Excellent. Brilliant. Great work to everyone there. That was superb. Right. So quickly, as we get nearing the end now, estimating roots and powers. I'm just going to quickly whiz through this. So for this one, if you were asked to estimate the powers, the values of these powers, basically what we do is we do it by comparing known powers. So for example, 5.3 is between 5 and 6. And I know what I can work out what 5 cubed is. 5 cubed is 125. And I know I can work out what 6 cubed is, that's 216. And 3/10 of the way along, I've got 5.3, and I'm cubing that. So 5.3 cubed, I'm going to go somewhere sort of between 125 and 216, and you could approximate sort of under halfway of that way along, so approximately say 150. And there'll be some tolerance for these questions. So in a very similar way, for this one, 4.4 to the -2, we can think about this as 1 over 4.4 squared. We've got to be careful here. So 1 over 4.4 squared is in between 1 over 5 squared and 1 over 4 squared. So that is 1/16, and that is 1/25. So somewhere in between, we've got 1 over 4.4 squared. So we could guess that one as a 20th. Okay, so it's a little bit weird, these questions, but there is, as I said, some leeway and some tolerance into how you do them. So we'll say accept an answer between this value and this value. Okay, does that method make sense? I do appreciate I'm going through this quite quickly, but does that method sort of make sense to everyone? Yeah. Cool. So what I'll do one more slide of this stuff, and then I appreciate we started a bit late and we've covered some really big ideas already. So I'm going to just quickly whiz through these last couple of little bits. So again, in a very similar way, we can estimate the value of roots by comparing to known roots. So can anyone guess what we would go between for these ones here? For square root of 30, what values could we compare? Well, let's think of our square numbers. Let's think, okay, I know the square root of 25 and I know the square root of 36. So the answer has got to be between 5 and 6. So square root of 30 is roughly in the middle. So I'd probably approximate 5.5. Yeah, brilliant. It's between 5 and 6, and there will be some tolerance because it is basically guessing. It's sensible, educated, mathematical approximating. So in a very similar way, think of our cube numbers. 27 is a cube number. So cube root of 27 is 3. And the next cube number is actually 64, which is 4. So cube root of 30 is very close to 3. So I would say maybe 3.1, 3.2 would be the cube root of 30. Obviously, you guys can evaluate it to whatever decimal places you want on the calculator. But this is sort of a little extra skill where there is some lenience or like tolerance on because it's essentially an educated guess. Just for that little skill that we've whizzed through there, if you guys can let me know how you felt about that. I know we spent a lot more time on the fractional and negative indices, and I think that was really worthwhile, especially looking at how crazily fast some of you were in the chat with that. That was brilliant. Lovely, that's brilliant. So there are some, for those that have downloaded the exam packs, there are some questions on this that you could try. So if I just finish with this one and then it leaves a spare one for you to do as well. Think of, we're estimating the square root of 60. So let's think of the square numbers either side of 60. You've got 49 and you've got 64. And that one is 8 squared. So, or I could rather, I'd write root 64 is 8. Root 49 is 7. So it's somewhere between 7 and 8 on my scale there. If I want root 60, it's probably a bit nearer to 8. So I would say root 60 is approximately 7.7. And again, then accept a few values for that, 7.7, 7.8. So maybe just over halfway. I'm making that clear. That would be really good. Right, so what we've done is we've really looked at understanding what a fractional power is doing, how to apply index laws, and also estimate values from known powers and known roots. A lot of you knew about something to the 0 is 1, something to the -1 is the reciprocal, something to the half is the square root. But rather than learning it as a rule, it is sometimes good to really try and appreciate why that ties in with the rules, and it helps us actually strengthen our understanding of the different rules. So that's lovely. Thank you so much for all of the kind of full-on engagement there that you've shown through the chat. It's made it very easy for me and really lovely to talk through this stuff with you. Just a reminder that if you are finding this useful, physics, biology, maths and chemistry, we are running on YouTube live like this every day at 5:30 at the moment. So hopefully that's beneficial for you and you're finding that useful. As I said at the start, we are going to give away 10 accounts for free if you sign up, and this competition is going to end on the 15th of February, which will come around in no time. So please do sign up if you haven't already and you are benefiting from this. That's great. I'm going to stop sharing that there. Thank you again, and apologies guys for the technical difficulties at the start. You've made that very easy and straightforward for me to deliver today, so I really appreciate that. I hope you all keep well and you'll keeping safe. I know it's been a strange start to the year, but really well done. Oh, okay, thank you, Sam. We'll make a note of that. Thank you, Samuel. That's lovely. And yeah, we'll edit that for next time. Cool. Well done, guys. Take care and have a good rest of the evening. Hopefully see you at one of these web classes again next week. Cool. Take care, guys. Well done, and thanks again.